Good morning. All right, I have a quick question and show of hands, as well as those of you in the chat, if you'd be so kind as to respond as well. How many of you have several exams coming up in like the next 3 days? Okay, so that's a significant portion of the class, and I'll check the chat as well. And I imagine that number would even be higher since we only have about half of the students here in the class. This is something that has come up here. Yes, okay. So I will have announcements in the lab. I'm going to try to figure out how to stagger some due dates. I had no idea until about yesterday afternoon that there were some students had up to 4 exams in the next 3 days. So I'm going to try to figure out a way to work around that. There were 36 submissions. There were 10 with not submission for the Creativity Challenge 4. I'm leaning heavily towards giving students who hadn't submitted about an 85% opportunity to submit it if you submit both creativity challenges by this coming Sunday. But I'm going to figure out how that works. So I just wanted to see how I don't have any decisions made because I didn't know precisely how that is. But that was news that I was not aware of. I thought I'd been clever and avoided it, but turned out no, it's not what happened at all. Okay, so what I want to do today is this is going to be the 4th out of 4 lectures in the series on graphs. We are going to revisit graphs towards the end of the semester. I'm going to do a 2-lecture kind of preview of the algorithms course, and we're going to discuss something called max flow and minimum cut then. But here, what we're going to discuss is minimum spanning trees and disjoint sets. As soon as the mouse wants to actually click through. Okay, so laying out the wiring on campus. So we've kind of discussed this before in terms of finding a path from one place to another, from Fitzpatrick Hall to the Hesburgh Library. But if I was trying to lay out wire, and all the wires originating from Fitzpatrick Hall, doing it like this in red would be a bit problematic. And the reason why is we're just using a lot of wire, it incurs a lot of cost, and it's a lot of redundant work, especially when you have 2 buildings that are really close to each other that we don't necessarily need to do this. So what if instead I came up with some way to go, I could hit all of the exact same places that I was wiring before with significantly less wire. So how can I minimize the total wire length, and how do I prioritize which wires I'd want to choose? So the way we're going to do this is something called a minimum spanning tree. So what we have on the right is a normal graph with weights, and we are going to define an origin, and the goal is how can we get to each possible node with the smallest possible weight. And if we can come up with that, where we have a graph that can accomplish this, this will allow us to be able to identify opportunities for cost improvement. So first what I want to do is I want to formally define the minimum spanning tree. And the minimum spanning tree, if we have 5 vertices, it will have 4 edges. So the goal is to come up with the total cost would be the minimum that we would require in order to be able to connect all of the vertices in the graph, and that's why we call it a minimum spanning tree. The mouse is not quite right. So I have this other thing about acyclic, and what I mean by acyclic is that the vertex can only be reached by one particular node. I can't go from A to D to C and then back to A. There's only one way to get to each vertex. So this allows us to be able to determine a schedule of elements. We can use this to be able to come up with wiring like we did before, coming up with a good set of roads. I've seen students in the past plan projects when they came up with a set of project dependencies and say, how are we going to come up with the best way to do this? Oh, hey, how about I just put all those into our minimum spanning tree code, run it, and oh, hey, look, there's our solution. This would be the most efficient way to complete this project. So these are different, all kinds of different cool opportunities that you can use to implement minimum spanning trees. So the question is, how do we actually do this? So the first thing we need to do is we need to come up with a way to initialize the vertex just like we've done with everything else. So we have to pick an origin. So in this case, we're picking A, and we have an origin, just like we know before, it doesn't have a parent, and it doesn't require any weight to get there. That's where we're going to start. And then what we're going to do is we're going to set everything else up as infinite. And then what we're going to do is we're going to, just like we're kind of like what we were doing with the shortest path algorithm, we are going to reduce the size. However, I'm going to put them into what is known as a priority queue. A priority queue is like queue, except you sort them by some sort of priority. So first in, priority out. And so what you're going to do for your creativity challenge this week is you're going to do one type of implementation of a priority queue, which is that you're going to design a sorted doubly linked list that you put it in, you push back, but then it sorts for you. And then based on the sorting, you'll get the element. The first element will be the highest priority. So you're going to write that in order to implement that, and you'll use inheritance and polymorphism to be able to run your tests. But also, I'm going to include the library standard priority queue. The standard priority queue implements this for us. And it does it largest to smallest, meaning that if I have 7, 4, 1, and 3, and I plug them all into the priority queue, it's going to go 7, 4, 3, and 1. Now, if you want it to be the opposite way, 1, 3, 4, and 7, you'd have to come up with your own sort of way to be able to sort them. And I'm going to show you a possible way to do that, and you'll kind of modify it in your creativity challenge. So then what's going to happen next is while P is not empty, so while the priority queue is not empty, what we're going to do is we're going to select the next vertex from that particular, the next set of edges from that particular vertex. And what I'm going to do is I'm going to do it like a breadth first search, and I'm going to update all of these to see what the weight is going to be. So here, initially, if it was just these 3, the simplest minimum spanning tree would just be 5, 4, and 5, right? And I should point out in my example, we're not including E here. So that would just be very simple. And once we do this, we're going to remove this element from the frontier. And we're going to call this frontier this idea of elements that we've already visited. And then what we're going to do is that we're going to update the weight. And the way we're going to do this is we're going to check to see if this weight is less than this one. So the way this would work, let's say this was 6 and this was 1, right? And we have an edge from D to B in theory. So what we're going to eventually do is we're going to evaluate the outgoing edges of D. And we would see that 4 and 1 would be less than 6, right? So therefore, that's the better connection. So going back to our analogy with the wires, we would want 4 and 1 to get to that location B instead of 5. We're achieving our goal of getting the wiring to the location with 1 unit less cost. And so we're going to go through this process and show you how everything works. Oh. That's a hint as to, I was making that for the homework assignment. All right, so here's Prim's algorithm. We start out and we initialize all of the elements that we haven't visited. So we're going to start at A, and then we're going to look at all the outgoing edges. So initially, oh, hold on, let me go back before the animation. So what you're going to see is I'm going to remove the element from the top of the priority queue. And then what you're going to see is the weights for B, C, and D become 5, 5, and 4 respectively. Because it's going to go from infinity to 5, 4, and 5. Everybody see that? And then I label the parent as A. And so now what we see here is there's our new priority. D has the smallest weight. So that's why we would want to evaluate it next. We move to the location that has the smallest weight we've needed to get to the next location. And if we think about this logically, this makes sense. If you were doing some sort of, if you had to choose 2 different ways to do a task, right? And one way was you're in your fantasy league and you choose a way in which you are good to win, you don't have to carry a basketball around, right? Whereas the most inefficient way is that you start a Mitchell and throws 3 interceptions and you have to carry a basketball. I don't know if you started Mitchell, but you get the idea. So there's an efficient way and an inefficient way. So if you keep doing the inefficient way, you don't want to do that. Likewise, with Prim's algorithm, if we know that I can start at A, and I have 2 edges that require a cost of 5 to B and C in this case, and I have another edge that costs 4 to get to D. Well, if I get to D in 4, that's less, and therefore it stands to reason that it's more likely that D would cost less to get to other locations because it already costs less to get to D. So that is why we would use the priority queue. And so that's why we'll start at D. So now D we remove. Now here's the interesting thing. D, let me go back. Note how before E is infinity. So from D, we're going to put this as 2, right? Because it doesn't have a parent. So now from D to E is going to be 2. And watch how E now moves to the front of the queue. If I look at C, right? Now what I have is I have 4 and 5, and I can compare those costs. Here it's 4, so now I'm going to reduce it. Here, 6 is more than 5, so therefore 5 is what we're going to choose. So now what we see here is that this edge is going to be part of the minimum spanning tree. So why do we choose to do that? The reason why is because not only is this allowing us to find the smallest weight that's incoming, but we can also identify the vertex that really should be our true origin. So even though A is going to be our origin, we're going to find out that we have a hub here at D. Does that make sense? So now it's like, hey, it makes a lot of sense. We wouldn't want to have our hub of wiring over at the hockey rink, right? We want to have someplace really close to the center of campus. And so what's going to happen is now that E is at the top of the priority queue, we're now going to analyze the outgoing edges. So we're going to have 9 and 5. Neither of those are going to be smaller. So E to B, 9 is not less than 5. And E to C, 5 is not less than 4. So here's the 5 there. So that means nothing's going to change. And so now we're going to evaluate from C. C has outgoing edges to E, D, and A. And so what's going to happen is we see that C has 5 here, D has 4 here, and A has 5 here. And so let's watch what happens. Oh, now we're going to update. Oh, I'm sorry, I'm going in the wrong direction, my fault. Now we see C here. Everything remains the same. Now we're going to evaluate everything from B, and none of those edges are smaller either. So let me quickly walk through this again just so I'm clear. We start out with everything infinity. No parents, no weights, right? Well, weight would be the largest possible. So we're going to start at A. We're going to evaluate all the outgoings. So we got B, C, and D, and currently those weights are 5, 5, and 4 respectively. We pick the smallest one. That's going to be the top of our priority queue. That's D. D has outgoing edges. We have edges from A, B, C, and D, right? And now 2 is less than infinity. Before we had 5, now we're going to go to 4 here. So we're going to update D's parent and C's parent from A to D. And then B, that was a 6. 6 is greater than 5. So we're going to see that B's parent remains A. Did we see that? Then E is now at the top of the priority queue. We evaluate all the outgoing edges. We don't have any edges that will be smaller. Then we evaluate C. Once again, C is going to remain the same thing. We don't have any parents at C. And then we evaluate B, because that's going to be at the end of the queue. And again, nothing changes. Which means that this particular table now is our priority queue. Sorry, our minimum spanning tree. So now what we can see is that initially we had A is everything, but as we moved on, we saw that's a really good idea to use D as our general hub, but we were able to reduce costs. So if we had 6 here instead of this one, we actually gained cost. So we see that? So by taking out that edge and leaving this one in, we've reduced our minimum spanning tree's cost by a value of 1. Hey, does anybody have any questions? Yes. All right, so that's a good question. So there may be multiple versions of the minimum spanning tree. If there's no clear one, it will just stay the same. So it has to be less than. Otherwise, in the code that I'm about to show you, if it's the tie, you just leave it alone. But you may have multiple minimum spanning trees of the exact same cost. But if there's a clear one with the lowest, that's what will definitely be returned. Is that your question? Awesome. All right, let me check the chat real quick. I don't see anything in the chat either. Okay, so let me take you through some code. And the first thing I'd like to do, apologize for not having that open, is this MST element. It's a struct, and it contains an index and a weight. And so what I'm doing here, you see I have my constructors with my member initialization lists. And what this struct is it contains a bunch of operators. And I'm saying if I'm comparing to, if I have MST left greater than or equal to right, in this case, my priority, I want this to be the lowest, right? So it was 2, 4, 7, and infinity, right? In standard priority queue, which I'm about to show you in a moment, it would actually put it in the exact opposite way because it starts from high to low. So what I have done here is I have created a structure where I can read in the elements that I wish to store to do my minimum spanning tree. And what you'll notice is this less than or equal to operator, it does the exact opposite. So this is greater than or equal to, it will return less than. It's greater than, it will return less than or equal to. If it's less than or equal to, it will return greater than. And if it's less than, it'll return greater than or equal to. Does everybody see how that works? So basically what I'm doing by reading the structure and storing my MST elements in this way, I can use the standard template library to perform this operation. And we'll do it without having to manipulate the library. Now, what you're going to do in your creativity challenge is you're going to create a priority element struct just like this, except you're going to make them work the right way. And then you're going to design a sorted dynamic array that sorts smallest to largest. Sorted doubly linked list that sorts smallest to largest. But that's how we can get around and make sure that our priority queue works correctly. So next thing I want to do is I want to go through my minimum spanning tree method that I've done in graph.h. So this lecture, this has the full graph. Everything that we've done up to this point, the graph.h in lecture 22, this is the complete graph. Everything that we've built from that really small graph1.h that just stored an adjacency list and left it alone. Now we're up to, let's see, somewhere here. Now we've included vertex class that we wrote, dynamic array, queues, stacks. We have a hash table. We have our MST element. I've also included standard priority queue. And then we've gone through all this and we've now have 886 lines of code. But let's take a look at MST. So what I've done here is I've created a graph, MST Graph. And that graph is going to contain the final minimum spanning tree. So MST, I'm returning that graph, and it's going to give me the correct result, just like we did with our topological sort with depth first search. So topological sort, that graph will give us the correct answers if we do a depth first search. And if we return a minimum spanning tree, we'll get the exact same answers for searching for things if we did a breadth first search. So the next thing I do is I set up my priority queue. I will need this to be able to run the algorithm. Next, I use my double hash here for my frontier. Have I visited it already? And this allows us to improve our runtime efficiency. So if I have a connection between the vertices, I would want to check if it's in there. Then I have parents, and this will allow me to do the same thing that we've been doing with the Sentinel, where we go back and put all of the elements and the edges into the minimum spanning tree graph that we'll return. And then I also have the weights. So from here, I initialize the origin and push it onto the priority queue. Now, we're not going to go over this in lecture, but if you wanted to run a minimum spanning tree from a specific vertex, you'd only modify it by putting in the vertex into the graph. So you would say minimum spanning tree and then give the index of the vertex in the adjacency list. So here in frontier, the first thing I do is I hash the origin and true. I then set the origin's parent to -1, so we can maintain the sentinel. And then I have its weight as being the smallest possible value that can be represented with a signed integer. So that way, nothing can possibly overwrite it. For this for loop, what I'm doing is I'm going through, I'm starting at 1. So origin was 0, and then I'm going from 1 to the end of the vertices. And what I'm doing in each one is I'm creating a almost said Mystery Science Theater 3000. Minimum spanning tree element, that index, and then the largest possible signed integer. So now we're as close to infinity as we can represent. And then the weight is also there. And now what I'm doing is I'm pushing each of those onto the priority queue, and then I insert into the frontier. So now, while the minimum spanning tree's priority queue is not empty, I then get that element from the top of the queue and then pop, just like we saw in the animation. And then I set that frontier of that current element equal to false. So remember, we have the index and the weight inside minimum spanning tree element. So then in this specific case, I'm going to do a for loop. And as I'm going through the for loop, what I'm going to do is I'm going to get the edge for each outgoing element from that vertex. So the cur edge, vertices, cur element index. So if I'm at index 3, it gets the vertex from that particular, and then get edge corresponds to the output. So if I have 3 outgoing vertices, I will have I0, I equals 1, I equals 2. And so I do this because instead of having to call this every time, I use a temp cur edge to simplify the coding. So now what I do next, I say if the weight is less than the current weight and the frontier of that destination is currently true, then what I will say is the weight of that particular destination is equal to the weight of that edge. So that's cur edge dot weight. So now we're picking the smallest one. And then parents, now we're setting it to that specific index. So now what we're saying is that, so cur element is the minimum spanning tree element, and cur edge is that specific edge that we got. So now what I'm doing is I have cur edge destination, cur edge weight. I create a new minimum spanning tree element, and then I push it onto the priority queue. And I keep doing that until we run out. So now what I do is, at the end, vertices.size, I add all the vertices to the minimum spanning tree graph because we want all the vertices to be in the minimum spanning tree as well. And then what I do is I iterate through that parent array. And if parents I does not equal 1, I set that edge equal to parents I and I. So the parent is the origin. I becomes the destination of the edge. And then weights of I is the weight that we found from our minimum spanning tree algorithm. And then finally, we return the new graph. Okay, so does anybody have any questions about this? Okay, so the first thing I'd like to do is I'd like to run make MST. And what we see here is I did a minimum spanning tree from that graph that I've been showing you from before with the incoming, from what we did for depth first search and topological sort, where all the edges are equivalent. This kind of gets back to the question from earlier. So here, because the origin was selected 4, all those edges will go out. Here we have an edge that goes to 3 from 1 and 2. And we see that because we're using breadth first search, this would be our result. And so we have a reduced minimum spanning tree. Through all these here. All right, so in minimum spanning tree 2, this is going to have the graph that I just showed you in the slides. So here we have the different weights, and we see that we ended up getting the exact graph that we were expecting earlier. And so 1 to 5 is from A to B, and 2, like so. Okay, so does anybody have any questions on minimum spanning trees? Let me check the chat real quick before we continue. Okay, so the next half, the remaining portion of the lecture is going to be about this idea of dynamic connectivity. So I've received several questions throughout the last 3 lectures about, well, what happens when not all the pieces are connected in the graph? And that's a really good question, and so we should investigate it. The idea of dynamic connectivity. We need to be able to evaluate if all the elements in a graph, all the vertices, are connected. And basically what that means is, can I find a path from one specific vertex to another? And so in this particular graph here I have at the bottom, is there a path from 0 to 9? And there isn't. Because we can prove this in multiple different ways. Remember how when we were building up our depth first search and our breadth first search approaches, we also accounted for a case where we didn't find a path. And so we can use that in this case. We can just say, are two vertices connected? We can just run depth first search or breadth first search from an origin to a destination. And we know that this can be done in what we're going to call big O of V plus E time. And so this because we go to each vertex and then we evaluate each outgoing edge. And if we go to the second one, we'll check this, but if it's already been visited, we're not going to evaluate it. So we would only evaluate each vertex once. We're going to evaluate each edge once. So the runtime for both breadth first search and depth first search is, and this is what's reflected in both the literature and in industry, is typically big O of V plus E. They'll even put it in absolute values. But the whole idea is that you're evaluating the number of edges and the number of vertices. So if you have what's known as a sparse graph, then you don't have that many connections, and therefore E is going to be really small. And if you have very few connections and a lot of vertices, then V becomes really big. And that's the control there. But ultimately, if you define them in both the same way, this ultimately comes out to big O of N. Right, so if our 0 and 1 connected, we'll say no. So now this other function that we're going to do is called union. And in disjoint sets, if we want to first find if there's a connection, and if not, connect them, this process we're going to call union find. Does that make sense? So the idea behind union find is before 0 and 1 were not connected. So first I would check to see if I can find a connection, and if not, I would just create an edge between them. That's the easiest way to do it. And so this idea of dynamic connectivity is we create a graph, and then we want to be able to evaluate the graph within our data structure to be able to see whether or not the specific elements we want to connect are actually connected. So still connected 0 through 7. And now union 2, 7 puts those together. And now what we see is we have 3 unique connected components. And these are known as disjoint sets. And so the more we have it, where they're connected, the fewer disjoint sets. So a very common interview question is, show me how to find the number of connected components in a graph. And we're going to solve that problem today. So connected, now 0 and 7 are connected, we see that's happy. 3 and 4 are connected. And you can use this, and I have a little diagram here. We're trying to figure out 2 vertices in a very large graph, and the larger the graph gets, the more our knowledge of data structures and things like Dijkstra's algorithm and Prim's algorithm and breadth first search and depth first search become very beneficial. So how do we model connections in our graphs? So this is where we're going to start applying some of our knowledge from discrete mathematics and kind of give you a little preview of the things that you'll see in a lot more detail in the algorithms course. So reflexive, P is connected to itself. I am me, right? Symmetric, in this particular case, if we say that the vertices are connected, in order to be able to perform this type of union find, we would have to have some way of ensuring that we can evaluate both P and Q and Q and P. So we had to say that they're connected somehow. So if it's directional, then we would say that P is connected to Q, where P is the origin and Q is the destination, but then we could say that Q is connected to P, where P is the origin and Q is the destination. And so then we say if P is connected to Q and Q is connected to R, then we say that P is connected to R. And we can do this with a depth first search or a breadth first search. If I say, all right, here's my origin, here's my destination, eventually that path will be found. So now a connected component is just basically the number of elements we have in the graph. So 0 is by itself. Here we have 1, 4, and 5. And here we have 2, 3, 6, and 7. And so let me throw this out to all of you. If I wanted to find the number of connected components in a graph, and the thing is, I can actually do this in big O of V plus E time. How do you think I would want to go about doing this? What's a potential algorithm that we've learned in the last 4 lectures that will allow us to be able to do this? We can make some modifications, but there is a good algorithm that will allow us to be able to find the connected components. All right, so let me start here. Maybe this will jog your thoughts. So if I wanted to see if 2 and 7 were connected, what algorithm would you want to use? Yes. Sure, we can use breadth first search or depth first search. So then I would say, I would use those connections. Let's say 2 is 3 is before 6 in the adjacency list, and we would find this particular path. But what if I wanted to figure out if there was a path from 2 to 3, 2 to 6, or 2 to 7? How could I use, and we're going to build off of depth first search here, is there an algorithm where instead of just looking for 7, it just keeps going and finds edges to every possible connected element? Yes. I'm sorry? So Dijkstra's shortest path, right? But you're on the right path. You're using the right kind of thinking. So Dijkstra's algorithm is shortest, but what does Dijkstra's algorithm do? What algorithm does Dijkstra's algorithm build off of? You're thinking it, right? Go back to it was one of the 2 that he said. What's that? Depth first search, right? So what other algorithm did we learn that builds off of depth first search? So instead of just stopping when we found something, it just kept going and finding in edges. What algorithm did we learn? Yes. Absolutely right. We can do a topological sort, and what's going to happen is I'm going to start at 0 and say, all right, give me a topological sort from that origin. And it's going to find nothing, right? So that means 1. So now what I'm going to do is I'm going to say find a topological sort when we start at 1. So what I can do is I can say, well, let's do 0, 1, 2, 3, 4, 5, 6, and 7, right? So if I do a topological sort and I just have some sort of incrementer, I can say, well, that's in the first one. And if I do a topological sort here, I start at 1, we'll just say that's 2, and 4 would be 2, and 5 would be 2, right? If anything's there, now I start at 2. 2 would be 3. Then I go to 3, that's going to be in the third one. 6, and then 7. And so now if I were to go to 3 and say, do I want to run this algorithm for 3? I would say no. And the reason why is because I've already found Everybody see that? So I just say if I would initialize all those to 0, and the moment if I fill it in there and I build it up, what's going to happen is now I say, all right, I've already found it, therefore I don't need to run topological sort from that. So that's where we get big O of V plus E. Because even though I'm going through all of these and kind of iterating, what ends up happening is if it's been visited, I'm not going to run another topological sort. So what ends up happening is I only visit each vertex once in a depth first search algorithm. So therefore, that is how we can say that this can be done in big O of n time. So let me take you through an animation. So a modified depth first search, we're going to take off the topological sort, and we don't need to return the path. But as you saw from that, from what I just drew up, that where we're going to actually have an array that contains which connected component that the two vertexes in. So therefore, not only can I return the number of connected components, if I wanted to modify this, I could say, all right, I'm going to, I can come up with a way to say which connected component each vertex is in. And I'm going to come back and ask you how y'all might do that in a moment. So let me go back to graph, and I have this public connected method. And what I'm doing is I'm just modifying depth first search. Here I have the same origin destination protection code. And then I just have a visited bool. I take out the parents array. And the reason why I don't need that is because I don't need to return a map. All I need to return is true or false of whether or not they actually are connected. So here I set them all visited to false, just like we did with depth first search before. Again, destination is origin, just return true, that simplifies it. And then I have a private method. And so instead of passing parents, I'm just doing the same thing with connected. So let me show you the private. Let me go all the way back up here. All right, so here's the private connected method. We see that we have the destination and the vert val, just like we did with depth first search before. And just like depth first search before, I'm calling a Boolean dynamic array by reference. But since in this case, I do not need to keep track of all the parents, we just took it out. Simplify the amount of code, simplify the amount of memory. Just like before, if we haven't visited it, we set it to true, and then we evaluate each outgoing vertex. And then we say if it hasn't been visited, we set that to true, and then we call it recursively, and this is where we get the depth first search. And here, instead of breaking, if that check that we've returned is true, that means we don't want to go to the next loop and evaluate it because we've already found it. So this improves some efficiency. And if we get all the way to the end, we return false. So in connected, I just call, I have this connected.cpp test code where I create a graph and I call check connected and I call the graph by reference and I have origin and destin. I say the vertices, origin, destination are, and if it returns false, when I call the graph connected, I just print out not, otherwise it's true. And so the rest of it is I call it's basically the exact same graph from the slides. What's going to happen when I run make connected is I'm going to say, here's my initial disjoint set. And we see that 0 and 1 are not connected, 2 and 1 are, 6 and 5 are connected, 3 and 8 are connected, but 3 and 9 are not connected because the only connection here is 4 and 9. So the union, what I do, it's relatively simple. I just say, if they're not connected, and then we're going to add an edge. So the way I do that, here's two different, for instance, if I have origin and destination, I say if they're not connected, and here I have bidirectional, and I say if they're one with weight. But I also have a version of the union function, union method, where I pass the weight there, and then I can create its connected edges as well. And so in this particular test code, what I'm doing is I check to see if they're connected. So in this particular union, here if I have a unidirectional union function, so we want to meet that requirement about being able to check P and Q. If it's unidirectional, meaning I don't want to put in two edges, I can say if it's not connected from origin to destination, and it's not connected from destination to origin, then I just add an edge from the origin to the destination. All right, so this now brings us to our lead code problem. So we have all the pieces put together. We've already even kind of gone through a solution. So now we know that we're running topological sort. We know that we only want to run topological sort if we haven't visited it in a previous topological sort, which improves our efficiency. And so here is a full animation that shows the solution. So we'll say 0, we'll update number of components, and then we'll update the component value in that particular graph. Then I would start at 1. Now I increment num components and put that value as 2. And then if I do depth first search, I would go to 2, 6, and 5. And all those get updated to 2. And then I have 3. It's 0, so I update it to 3. And then I do depth first search to 8, and I update that to 3 as well. Then I check 4. It's 0, so I update num components to 4. And then I do depth first search to 9. And 5 is there, 6, 7, and then we've caught it, 8 and 9. They're not 0, so we don't do depth first search. And so we step through, and now we can actually say what the connected components are. And so I've done this with a modified connected. So here I'm going to show you top sort, get components. All right, so num connected, obtain the number of connected elements. So if vertices size is equal to 0, just return 0. Otherwise, I have that dynamic array of connected elements, just like I showed you in the animation. And then I did a for loop. I set everything equal to 0. So now I can say if it's 0, we want to do a depth first search. And so now I also have the number of connected components here. And then I iterate through each vertex. And if it's equal to 0, I do numcom ++. And then I have this get components method, which is a modified topological sort. And what it is it's a private method. It's basically the exact same thing as we've done before, except if it's not visited. So we do the one thing, we say visited val is equal to num component. So this is why we can say 1, 2, 3, 4, and 5 for 5 components. And then we say if it's visited is equal to 0, so we can keep track of all those values. So let me run num connected. And in this particular one, what you're going to see is it has several tests. And we initially start out with a pretty large graph that has 5 connected components. I run all the tests, and we see that the graph initially says 5. And then when remember 0 is by itself, so I run the union of 0 and 1. And we now see that we have an edge from 0 to 1. And when I run the algorithm again, it has 4 connected components. When I run the union of 2 and 7, well, it's already connected. So therefore, 2 and 7, now I'm connecting 2 of the components, and now we're down to 3. I apologize, 3 and 8 are already connected. So when I run the union of 3 and 8, it's not going to add an edge at all, which means when I run this again, it's going to have the same number of 3 connected components. 3 and 9 were not connected, so when I run that union, I can now check all of these, and we're now down to 2 connected components. All right, so does anybody have any questions about that? Okay, so it is time to dismiss. I see there's a couple of quick questions in the chat. Stack and BFS, so Tiani and Fankong were correct. I will have how we're going to get through the next 2 weeks. I do want to have the creativity challenges done by this coming Sunday because we're starting the pre-internship next week. So on that note, it is 11:16. You are all dismissed.